This topic is about the fundamental theorem of calculus and how the area under the curve is found by the process of integration. So the area under a curve between two values of x can be approximated by a series of rectangles. So if we have a function that looks like this, then if we split it up into rectangles, we can use these rectangles, the sum of these rectangles, to sort of approximate the area under the curve. Okay, so the area can be approximated by the sum of these rectangles. So the area is approximately equal to sum of yi, so yi would be basically the height of each rectangle, times by delta x, which is basically the width of these rectangles, where yi is the height of each of these rectangles, and delta x is b minus a divided by n, is each rectangle's width. So if you're trying to work out the area between b and a, then it's b minus a divided by n, where n is the number of rectangles that you have. Okay, and also you can split up differently, so n can be however much you want. So for example, we have split up into 1, 2, 3, 4, 5, 6, 7, 8, 9. N is 9 in this case. If we draw something similar, like so, but we have n is equal to 5, we can split up into 5 rectangles instead. 1, 2, 3, 4, 5. So imagine this is A and this is B. And we're using, again, these rectangles to estimate. Then obviously this one, the first one, would be a better estimate because the number of triangles is more. So the more triangles you have, the better estimate it is. So here we've got 1, 2, 3, 4, 5. Okay, so this is what you should, this is quite important. So make sure you memorize this. Okay, let's do it in a different color. So the area is approximately equal to the sum of these rectangles, which is sum of I is equal to 1 to n, yi times delta x. Okay, another thing to know is defining the integral notation. Okay, this is the process by which the area under a curve f of x is found. So if you want to find the area under the curve, it is the integral of b to a of f of x dx. Now, we do not know how to do this at the moment, but we know this is used to work out the area for a given y is equal to f of x. So what we want to do is we want to link these two area equations or approximations together, so we can see what we do for each one. We can relate them together. Yeah. So you want to connect the two different equations together. That's the aim of this first part of this lesson. Okay, so there's a fundamental theorem of calculus. Let's go through it. Differentiate the area function from first principles. So in this proof, we're going to use differentiation from first principle. So he's using differentiation from first principles. You need to remember that f dash of x is equal to limit h tends to 0 of f of x plus h minus f of x all over h. Okay, so we're going to use this. So imagine we have a function. Okay, so the function goes like this, and then we have a point x. So we have a point x here, and then this would be f of x, the y value, corresponding y value. If we increase x by h, then that point, the x value of that point will be x plus h. This is y is equal to f of x. Then what we do know, if I use a different color, so this would be, the orange represents area of x, okay, and the green represents, so all the extra part, so all the orange part plus the extra part is area of x plus h. Okay. Okay, so what we do know is using differentiation from first principles, so using the formula, then we do know that a dash of x will be equal to limit h tends to 0 of a of x plus h minus a of x all over h. What we've done in the general formula is replace the f with a. This is the same thing as limit h tends to 0. So what we're doing is, if you look at the numerator, you're doing the green part. So this is just the green part. So if I use, this is just the green part, and that is just the orange part. So all you're doing is the green part take with the orange part. So what you end up with is basically only, if I use a different color again, purple, you're only getting left with this part. Okay, now this is the excess part, this triangular part, which tends to 0 as h tends to 0. So it will disappear, that part. So all we're left is really with is that triangle. Now that triangle is just y times, so length times width, which is just f of x times h. Because that triangular part will disappear as we obviously make h closer and closer to 0. Remember, we're trying to make h get closer and closer to 0. So f of x times h is just what remains over h. The h and the h cancel out, and f of x no longer has h involved, which is just f of x. So when you differentiate the area function, we get f of x. So therefore, a dash of x is equal to f of x, i.e. the derivative of the area function gives us the original function. So when we differentiate the area, we get the area function. Therefore, antiderivative of f of x gives you the area function, which is the area under the curve. So the antiderivative of f of x gives you the area function, and that's the main takeaway from here. So what has this shown about the area under the curve? So what we now know is that when we differentiate the area function, a dash of x gives us f of x, which is the same thing as saying when we differentiate a with respect to x, we get f of x. We also know that a is equal to this weird sign, which is the integral from b to a of f of x dx by definition, which is the process of integration. Therefore, to find the area under the curve between x equals a and x equals b, we need to find the antiderivative of f of x, which is integration. All this summarizes to that fact that a, which is equal to the integral of b to a f of x dx, is the antiderivative of f of x, which is the capital F of x of b to a. So it's the antiderivative of f of x, which is the capital. Remember, in the last lesson we said that is capital F of x. So antiderivative is called integrating. Let's call it. It's called integrating. Finding the antiderivative is basically called integrating. Okay, so let's go through some examples. It says find the area bounded by the curve f of x is equal to x squared minus 6x plus 9, the y-axis and the x-axis, and the line x is equal to 3. So let's do a rough sketch. So x squared minus 6x plus 9 is equal to, if I factorize it, it's the same thing as x minus 3 times x minus 3, which is equal to x minus 3 all squared. Which means if I sketch it, it's a quadratic with a double root at 3. So like that. So y is equal to x minus 3 all squared. Find the area that is bounded by the y-axis. So let's use a different color to highlight it. So y-axis is here, the x-axis is here, and the line x equals 3. So the line x equals 3. So basically what we're trying to find is all of this. So bounded by the curves, of a curve, and the line x equals 3. So it's this part. We're trying to find this part. So this is the same thing as integrating between x equals 0 and x equals 3. So that is the same thing as integrating between 3 and 0. So because 3 is the higher number and the bigger number you put at the top is the upper limit and 0 is the lower limit of the function x squared minus 6x plus 9 all dx. Okay. Now remember writing the integral. So this is the integral, which is the sum of the rectangles. So it's the area function. Between 3 to 0 of x squared minus 6x plus 9 is the same as finding the antiderivative. So you're just integrating it, which means, remember, x squared, you increase the power, which is cube, divide by the increase, minus 6x, increase the power by 1, 2, divide by 2, plus 9x between 3 and 0. Now, all you need to do is simplify it. So when you simplify it, you get a third x cubed minus 3x squared plus 9x between 3 and 0. The first thing you need to do is substitute 3 in. So a third times 3 cubed minus 3 times 3 squared plus 9 times 3. And then substitute 0 into the same equation. Now you should realize when you substitute 0 into this equation, you're just going to get 0 because it's got a multiple of 0 in every single term. So it's just going to be 0. Okay. What you end up getting is the first term is 9, second term is minus 27 plus 27, which gives me a total of 9. Now you can write 9 units squared if you want, but 9 is enough. But if you want to, you can write 9 units squared because the area we're finding. So 9 is the answer for that. Okay, let's look at another example. Find the area bounded by the curve f of x is equal to x squared plus 4x plus 4, the x-axis, and the line x equals 0 and x equals 2. So x squared plus 4x plus 4 is the same thing as x plus 2 times x plus 2, which is x plus 2 all squared. So when I draw this out, sketch this out, it's a quadratic with a double root at minus 2. It's positive quadratic, so it looks like so. We don't care about where it intercepts the y-axis at the moment. Okay. Let's make it longer. So we're trying to find bounded by the curve, the x-axis. So the x-axis is here. The line x equals 0. So the line x equals 0. So x-axis. The line x equals 2. So somewhere here we've got 2. Somewhere here we've got 2. And the curve. So it looks like we're looking for this area, which is bounded by 0, x equals 0 and x equals 2. So what we're doing is we're integrating between 2 and 0, x squared plus 4x plus 4 dx. So the integral of x squared plus 4x plus 4 between 2 and 0. So first I need to integrate it, find the antiderivative. So increase the power, divide by the increase the next term by 1, divide by the increase again, and divide by the increase by 1. Between 2 and 0. When we simplify this, we get a third x cubed plus 2x squared plus 4x between 2 and 0. Now I need to substitute in first 2, a third times 2 cubed plus 2 times 2 squared plus 4 times 2. Again, if I substitute 0 into the whole equation, so the whole expression, sorry, I get 0. So I'm not going to write that all out. So when I do a third times 2 cubed, I get 8 over 3. 2 times 2 squared is 8. 4 times 2 is 8. That gives me 56 over 3 when I put this in my calculator. Okay, find the area bounded by the curve f of x is equal to 4 minus x squared and the x-axis. So 4 minus x squared. 4 minus x squared is the difference of squares, so it's 2 minus x times 2 plus x. So when I draw this out, x, y, there's a root at minus 2 and a root at 2. Okay, so we're trying to find, it's bounded by the curve, so curve and the x-axis. So it's basically this part. Okay, so we're integrating between x equals minus 2 and 2. So 2 at the top, minus 2 at the bottom, 4 minus x squared, all dx, which is the same thing as when you integrate it, you get 4x minus x cubed over 3 from 2 to minus 2. So what we need to do is substitute 2 in first. 4 times 2 minus 2 cubed over 3 minus 4 times minus 2 minus minus 2 cubed over 3. Okay, so the first one gives me, when I do 4 times 2 take away 2 cubed over 3, it gives me 16 over 3 for the first term, minus, for the second term I get minus 16 over 3. So put this into your calculator, see what you get for each one. And when I do 16 over 3 take away negative 16 over 3, I get 32 over 3. So that would be my answer. Find the area under the curve y is equal to root x. The x-axis and the line x equals 1 and x equals 4. Okay, root x. So if I'm sketching this graph, root x looks like this. Y is equal to root x. So all I'm trying to find is the x-axis, the line x equals 1 and x equals 4. So somewhere here, it's a rough sketch, 1 and 4. And the curve. So we're looking for this part. Okay, so all we're doing really is we're integrating between 4 and 1 root x dx, which is the same thing as integrating x to the power of a half. X to the power of a half dx. When we integrate this, we increase the power, so it's x 3 over 2, divide by the increase, which is 3 over 2, between 4 and 1. As soon as we integrate it, we don't write dx, write dx, and we don't write the integral sign. Okay, which is equal to 2 over 3 x to the power of 3 over 2, between 4 and 1, which is 2 over 3. First substitute 4 in, and then subtract when you substitute in 1. Okay, so the first term gives you 16 over 3. The second term gives you 2 over 3. 16 over 3 take away 2 over 3 is equal to 14 over 3. Find the area bounded by the curve y equals 1 over x squared, and the x-axis and the line x equals 2 and x equals 5. So if we're thinking about that, 1 over x squared looks like so. Y is equal to 1 over x squared. So what you're trying to do is the line x-axis, which is here, x equals 2 and x equals 5. So 2 and 5, and the curve. So you're trying to find this part here. Okay, so you're integrating between 5 and 2, 1 over x squared dx, which is the integral of between 5 and 2 of x to the minus 2. dx. As soon as you integrate it, remember square brackets. So increase the power, which is x to the minus 1, divide by the increase, which is minus 1. No dx anymore because we integrated. Now put 5 and 2. Okay, which is the same thing as minus x to the minus 1 between 5 and 2, for 5 and 2. So it's the same thing as minus 5 to the minus 1, take away minus 2 to the minus 1. I don't know if that's clear, so let's try writing that again. Minus. So I get minus the fifth for the first term, take away minus the half. Okay, which gives me negative 0.2 plus 0.5, which is equal to 0.3, which can be written as 3 over 10. Okay, find the area of the region bounded by the x-axis, the line x equals minus 1 and x equals 1, and the curve f of x is equal to x squared minus 2x plus 2. Okay, so x squared minus 2x plus 2 doesn't look like it'll factorize, so I'll complete the square. So I get x minus 1 squared, take away 1 plus 2, which is x minus 1 squared plus 1. So vertex at 1, 1. So it looks like so. So it's a parabola x, y at 1, 1. You have a vertex. So it looks like so. So the vertex is at 1. I don't know. 1. Okay. So you're trying to find the area of the region bounded by the x-axis. So the x-axis, x equals 1, x equals minus 1, and the curve. So, oops, undo. And the curve here. So it looks like we're finding this area, which means we need to integrate between 1 and minus 1, x squared minus 2x plus 2 dx. Okay, as soon as we integrate, we have square brackets, so increase the power, divide by the increase, minus 2x squared, divide by 2, plus 2x, close the square bracket between 1 and minus 1. Okay, if I simplify that, I get a third x cubed minus x squared plus 2x from 1 to minus 1. So first substitute 1 in, so a third times 1 cubed minus 1 squared plus 2 times 1. Subtract when you substitute minus 1 in, so a third times minus 1 cubed minus 1 squared plus 2 times minus 1. When you input the first bit into the calculator, you end up getting a third minus 1 plus 2, which is 4 over 3. Subtracted from when you input the second part into your calculator, you end up getting minus 10 over 3. When you do 4 over 3, subtract minus negative 10 over 3, you get 14 over 3. That's it. Okay, so just to summarize notation-wise, because there's a lot of notation involved here, the area of the region bounded by the line, the x-axis, the line x equals 1 and x equals 3, and the curve f of x is equal to x squared minus 2x plus 2 is the same thing as writing this out. Now, you can always sketch it and just make sure that it's the right thing, but it's the same thing as writing that out. So the integral means the sum of all these rectangles. So that elongated s means sum of. That's why, because when we're doing integration, we're actually thinking of these little rectangles and adding up the sum of all these areas of the rectangles. So that's why we use this sign, which is the integral of. Okay. Second thing is the area function can be approximated, remember, by the sum of these rectangles. So sum of I equals 1 to n of yi times delta x, but it's also equal to the integral of b to a f of x dx. So they're the same thing. So you can write it out. They both mean the same thing. So this process is called definite integration. So definite integration when your integral has limits. So do you see how the limits are these numbers b and a at the top, yeah, and bottom. So b of the integral sign. So when it has limits, then the process is definite integration. You're going to get an answer which is a numerical. The process of just finding the antiderivative is called indefinite integration. And remember, in the last lesson, when we're doing indefinite integration, your integral would not have limits, and you need to include the constant. Remember, we were adding c to your answer at the end, so to your solution. So constant integration for indefinite integral. So you have f of x dx. When you integrate that, you're going to get an answer and then plus c. Okay. This formula is very important, so make sure you remember it, because it can come up in an exam. They might say, what does this mean? And you have to say, obviously, it's the same thing as the integral of the function.